To continue now, we have to Professor Victor Hugo introduce to Professor Bingyu Zhang. You can start, Victor.
So, good afternoon, everyone. It's a pleasure for our seminar to welcome Professor Bingyu Zhang from the Department of Mathematics of the University of Cincinnati. Professor Zhang will talk about the effect of dispersion and dissipation in a class of evolution equations. Let me tell you a little bit about Professor Bingyu Zhang. Professor Zhang started his career in the 90s when finished his PhD thesis at the University of Wisconsin in Madison under the supervision of Professor David Russell. Zhang is an expert in control theory of partial differential equations, nonlinear dispersive waves, electromagnetic waves, nonlinear analysis, and applied harmonic analysis. He visited several universities until became a full professor at the University of Cincinnati. And with more than 95 publications, Professor Zhang has around 2,000 citations in MathSciNet, 6 PhD students, and several collaborators around the world. Today, Professor Zhang will give us this great opportunity to attend his lecture entitled on some joint effects of dispersion and dissipation of a class of nonlinear evolution equations. So, Professor Zhang, you can start.
Well, thank you very much, Victor. I also like to thank the organizers who give me this opportunity to present my recent work on this very good seminars. Thank you. Okay, what I'm going to present here our recent work on some joint effects of dispersion and dissipation of class of nonlinear evolution equations. It is a joint work with Su-Min Zhang of Virginia Tech, Xin Yang of University of California at Riverside, and also Lin Zhong from University of Cincinnati. I'll start my introduction here. First, let's consider this class of nonlinear evolution equations. Okay, so here alpha, delta, beta are real constants. It includes the well-known KdV equation. In the case of alpha, beta equal to 0, that's KdV equation. It is a classical nonlinear dispersive wave equations. Here, I want to emphasize a role of the term alpha u sub x is dispersion. Okay, that's dispersion. Including this class, also we have the viscous Burgers equation. Okay, we think alpha is 0, you get a Burgers equation. As you can see, the role of the term beta u sub 2x is dispersion, dissipation if beta less than 0, and but if beta is greater than 0, then you get anti-dissipation. And as for the equation itself, if alpha beta not 0, but with beta less than 0, we call that KdV-Burgers equation. Okay. And here, both dispersion and dissipation presented in the equation. Okay. Without the loss of generality, we can assume all the coefficients is 1 or minus 1. So we have here the KdV equation, the Burgers equation, here's minus 1. And the KdV-Burgers equation. Okay, this is dispersive wave equation. This is a dissipative equation. This has combined both dispersion and dissipation. The question we're interested here, we are looking for: are there any properties that the KdV-Burgers equation possesses, but neither the KdV equation nor the Burgers equation have? If such a property we can find, it certainly is due to joint effects of dispersion and dissipation. We are going to look at this issue from two aspects of the equation. One is well-posted of Cauchy problem. Another one is Cato smoothing properties. Now let's come back first, talk about well-postedness of the Cauchy problem. Here, let me give you a brief review of what's the definition of well-postedness. Okay, consider the abstract Cauchy problem. Here, A is a linear operator, N is nonlinear operator. And the post on the index Banach spaces X sub S, as X sub X1 is continuous embedding into X S sub 2 if S sub 2 is less than S sub 1. Okay. Here, we say the Cauchy problem is well-posed in the space XS if, given initial data in this space, there exists a unique solution belongs to this function space. And the corresponding solution map from W0 to W is continuous from this space X sub S to this solution space. Okay. And usually we call this kind of well-postedness C0 well-postedness because solution map is only continuous. However, if the solution map instead of just continuous also C1, then we say that C1 well-postedness. If solution map is C2, then we say C2 well-postedness. Moreover, if the solution map is real analytic from this space to this space, we say this is analytically well-posed. Now, the question is for abstract Cauchy problem here, the question is for what value of S the Cauchy problem is well-posed in this space. We're looking for all those S's, S to make sure, and the Cauchy problem is well-posed. Now let's go back to consider the Cauchy problem of the KdV equation on whole line R. Okay, for what value of S the Cauchy problem is well-posed in the space HS of R. This is a well-known classical problem, and it started as early as 1960s, last century, and just recently the study have a happy end. Okay, so here I just list a few landmark results for this study. One of them, first one I put it here is the work of Bona and Smith. They show the Cauchy problem is C0 well-posed for any S greater than equals 2. Another landmark result is due to Cable. He just used semi-group approach and they show that Cauchy problem is C0 well-posed for S greater than 3.5. After that, the harmonic analysis has been played a major role here to study this Cauchy problem. And then, first one, the Koenig, Bunce, and Vega show the Cauchy problem is analytically well-posed for any S greater than 3/4. Now, after that, Bergan showed that for analytically well-posed for S greater than equal to 0. Then, Koenig, Bunce, Vega show this is analytical well-posed for S greater than -3/4. Okay, and then Christine Coliando and Tao show it is analytical well-posed for S equals equal to -3/4. And also we know the problem is not analytical, is ill-posed for any S less than -3/4. I mean, analytically ill-posed. Then there's another work by Keening and Wissam. They show the Cauchy problem is C0 well-posed in the space HS of R for S greater than equal to -1. So that under the study of this problem, because for any s less than -1, we know that it is ill-posed. So this is Cauchy problem for the KdV equation. Next, let's consider the Cauchy problem of the Burgers equation. Okay, and back to last century, 1996, Daniel Dix showed that this is analytically well posed in space HS of R for any s greater than -12. And when at the same year, and Dirk Randolph and showed that, okay, that's also analytical well posed for s equals -12. And also Daniel Dix showed that if s less than -12, it is ill-posed. So this is a sharp result. Okay. Then how about the KdV-Burgers equation? And here Nonlinear and Rubel first show that this is analytical well posed of any s greater than -1. And then almost 10 years later, Nonlinear and Vinto show that, okay, for the case for s equals -1, it's also analytically well posed. This is sharp results because for any s less than -1, it's ill-posed. In summary, here for KdV equation, we know is analytical well posed for any s greater than or equal to -3/4. For Burgers equation, is analytical well posed in the space HS of R for any s greater than or equal to -12. Now, for KdV-Burgers equation, as a presentation of dispersion and dissipation, then it's analytically well posed of s greater than or equals to -1. Certainly, this is joint effects of dispersion and dissipation. Next, we consider Cadle smoothing properties. Consider the Cauchy problem of KdV equation on the whole line. We know the solution U is as smooth as its initial value 5. That means 5 initial value belongs to HS of R if and only if U at any time belongs to HSR. Okay, you know this Cauchy problem of KdV equation whole line is well posed both forward and backwards. So solution is as smooth as its initial value. You know, here's a question: can solution U be smoother than its initial value? Based on this one, we'll say, yeah, probably not. However, it's quite surprisingly, the Cadle discovered that, in fact, solution can be 1 order smoother than its initial value, but only locally. Okay, it's not globally. Here's it's +1, but locally. When you restrict the solution in compact domain, its regularity is s +1. So 1 order than smoother than its initial value. But of course, you have to restrict the compact domain. You have this property. So this one is called the local Cadle smoothing. And it turns out this kind of smoothing is a common feature for all dispersive wave systems. Let's consider this one. And all this assumption basically means this is dispersive wave equation with all order n. Okay. Then Constantin and Saul show that if initially that belongs to HS of R, then the solution is m-1/2 smoother than its initial value, of course, locally. Okay. And also Constantin and Saul pointed out here, the solution is m-1/2 order smoother than its initial value locally. Okay. Now, m is order of this differential operator. Okay. Secondly, the smoothing has nothing to do with space dimension n. Okay. Third, the smoothing is not caused by the nonlinearity. Okay, not just in the KdV case, basically it's caused U sub x does not play any role there. All right, let's go back to KdV equation. Okay, now this one, for initial data is L2, then solution U is H1 locally. So one order smooth, that's initial value, because M is 3, 3 minus 1 is 2 divided by 2, that's 1. Okay. Now, next question, is this Cato smoothing property sharp? Can we do something better than that? The answer, okay. And then we have something called sharp Cato smoothing. Okay. And the K-response data take this into account. They show the following things. If initial data is L2, in homogeneous term is L1 about time, L2 about the space, then solution is one order smoother. However, U sub x belongs to this space. L infinity about the space, the spatial variable. Okay. As comparison, this is Cato local smoothing. You can have U sub x belongs to L2 about the space variable x as L2, but sharp Cato smoothing here is L infinity. So jump from 2 to L infinity. Okay, so of course, and this local Cato smoothing part of will follows from this sharp Cato smoothing due to K-1 and Vega. There's another Cato smoothing called double sharp Cato smoothing. K-expanse data also show that if F is initial data 0, if F is L1 in the space variable, L2 in time variable, and instead of solution is instead of one order smoother, and it becomes 2 order smoother. So we call that double sharp Cato smoothing. Okay. As comparison, you can see this is a sharp Cato smoothing, but here F just L1 bar time, L2 bar space, then you only have the solution is only one order smoother. However, you can see if you change this L1 bar space variable x, L2 bar time, this switch, right? Then you get a double smoothing. So we call that a double sharp Cato smoothing. This work due to K-expanse Vega. And then another Cato smoothing, we call that strong Cato smoothing. Okay, same things here, and this is the result due to K-expanse Vega. If F is Lx, L1 about x, L2 about time, and then U sub x belongs to continuous about time and the L2 about space x. As a comparison to that sharp Cato smoothing, sharp Cato smoothing basically said, okay, and then you can have this, or I'm sorry, not sharp, this Cato smoothing, and then basically you have L2 about time, L2 about space. This is a Cato smoothing, right? But this one you can see about time jump from L2 about time becomes L infinity about time. It's continuous about time. So that recognize it jumps. Okay, and also about the space variable. This L2 is globally. Here is locally. Here is globally. Okay, but of course, the condition F are different. For this F is L1 about the space variable, L2 about time variable. If you switch it, L1 about time variable, L2 about the space variable. For this one, you only get the Cato smoothing, but for this one, you got a strong Cato smoothing. Okay, strong Cato. By the way, both results are sharp. Okay, that's we know the sharp Cato smoothing property in control theory. In the people in control theory community, we know that is known as the sharp trace estimates. It plays an important role in studying non-homogeneous boundary value problem and also controllability and stabilizability. Okay. Next, we tend to consider Cauchy problem posed on a periodic domain. The previous discussion is for Cauchy problem posed on the whole line R. Now, how about on a periodic domain? Say like this one. KdV. The T is torus, right? It's torus as pure domain. And the KdV is Burger's equation and the KdV Burger's equation. Okay. How about the solutions of this Cauchy problem in the pure domain? Do they have any kind of smoothing, Cato smoothing property? No. First of all, the KdV equation posed on the pure domain possesses neither the Cato smoothing property nor the sharp Cato smoothing property. Now there's no, you don't have any kind of Cato smoothing. The reason for that is because pure domain is compact domain. The solution Cauchy problem is well posed forward and backwards. So any kind of local Cato smoothing becomes global, it's compact domain. So that against the principle here is well posed forward and backwards. So we know that you don't have any kind of Cato smoothing property. This Cauchy problem of KdV equation on a periodic domain. Now, how about the Burger's equation? Yeah, and we know that because this dissipation here, immediately it has a solution is one order smoother than its initial value, so belongs to this space. So this is kind of, you can say, this is a Cato smoothing property, right? However, it does not a sharp Cato smoothing because this is the best trace result. You had to a half minus each. Yeah, this is the best you can get. Okay, so for Burger's equation, basically, we don't have sharp Cato smoothing property. Now, how about the KdV Burger's equation? Posed on pure domain. Now you have dissipation, you have dispersion, right? So remember, we are looking for some Jordan effects of dissipation and the dispersion. Okay. Now, does it possess any Cato smoothing property? Okay, we consider this problem in our early work. So here we consider the KdV Burger's equation. Here, g of x is smooth function, but it could be with compact support, with support, non-empty support could be a very small open subset of this pure domain. Okay. Then we can prove this result. If G is positive, non-negative, so we have dissipation, okay, but only acting on small parts of domain T. But as long as this part non-negative, then you have a Cato smoothing. So solution is one order smoother than the initial data. That's Cato smoothing. Next, then we show if G of x is constant, it acts on whole periodic domain and is constant. And then we have sharp Cato smoothing. Okay, this work appeared in the 2021. But of course, we're not very happy about this one because why this one has to be constant in order to get sharp Cato smoothing? Okay, how about this one? Can we get sharp Cato smoothing for this case? Not just this case. So we're not very happy about these results, so keep working on that. And recently, we consider this more general case. So we have KdV kind of this nonlinear evolution equation with this dispersion and dissipation, but we have variable coefficients alpha xt and beta of xt. And here, beta is just have a support, non-empty support in the pure domain T. Okay, but here we only, but the beta could be positive, could be negative. We just assume the following things. We call that weak dissipation. Kind of beta over absolute value of alpha, its mean value over this pure domain T is greater than 0. So beta itself could be some point positive or could be negative. So at some point is dissipation, at some point is anti-dissipation. But overall, mean value is greater than 0. So we call that weak dissipation. Okay, weak dissipation. Then we prove the following theory. Okay. With this weak dissipation, then it possesses the sharp Cato smoothing property. So we improve our early work. Okay. So sharp Cato smoothing. So one. And then we also show the nonlinear part of the solution U of this nonlinear evolution equation with this assumption possesses strong Cato smoothing. So if you initial data HS, then U minus V is solution of a linear problem. U is solution of nonlinear problem. So the difference between solution of nonlinear problem and solution of linear problem are called the nonlinear part of the solution U. Has a strong Cato smoothing. So as a continuous about time, HS plus 1. Okay. So this is strong Cato smoothing. Then next one is the nonlinear part of the solution, in fact, possesses a sharp double Cato smoothing. So it's 2 orders smoother than its initial value. Okay, sharp 2. So that basically answers our question here. Of course, all the 3 results, Cato smoothing properties, is due. You don't have that for KdV equation. You don't have that for Berger's equation. But due to the presentation of both dispersion and dissipation, then we have those 3 Cato smoothing properties. Okay, of course, that's joint effects of dispersion and dissipation. Okay. Now, next, how do we prove that? Okay, first, now as Constantine and Shaw pointed out, those kind of smoothing property do not caused by nonlinearity. So what do we do here? We just need to consider the corresponding linear system. Forget about the U sub x, only consider the linear parts. I put a forcing term F here. We only need to prove the following 3 propositions, getting linear estimates. Okay. So if initial data phi belongs HS, F belongs 1, then we have a sharp Cato smoothing. Okay, for this linear problem. Next is we have sharp double Cato smoothing. If F belongs L2, remember here, if F is L1, you only get a sharp Cato smoothing. But if F is L2 bar time instead of L1 bar time, then you get a double Cato, sharp Cato smoothing. Okay, sharp double Cato smoothing. And also, if F belongs to L2, you have strong Cato smoothing. U belongs to L0 to HS plus 1. Okay, so we just need to prove this 3 proposition for linear system. Then, of course, then we can get the results for this theorem 1, 2, and 3 for nonlinear system. Next, is the outlines of the proofs. This is an equation with variable coefficients, right? So first one, naturally, we try to do some variable transformation to get rid of this coefficient, variable coefficient, make it a constant. Okay. First what we do here. Now this is posed on the periodic domain T, right? Equivalently, we can rewrite as the periodic boundary value problem like this. U0 t equals U1t, U sub x0 t equals U sub x1t, U sub 2x0 t equals U sub 2x1t. So this is periodic domain T. This is basically the equation posed on finite interval U1 with periodic boundary condition. They are equivalent, we know that. Okay. Next, we make transformation. Is tau equals eta t defined by this, right? And the y just equal this. Remember here, alpha are coefficients here, and beta are coefficients. First, we try to get rid of this alpha, right? We make this kind of transformation, and then you can do the calculation. That ends up the equation like this. So this is third order term. The coefficient alpha xt disappear now. That becomes 1. Okay. So we have tau, t becomes tau, x becomes y. Okay, and then here, the mean value of the coefficient for v sub 2y is equal like this. Okay. Of course, that's a little bit tedious calculation. You can verify that. That's straightforward calculation. Now we still have here a variable coefficient. We try to get rid of that too. Okay, so without the loss of generality, we come back, think about it, change t, tau back to t, y back to x. Okay, so just simplify our notation. Okay, and then we consider this type of equation with variable coefficients appeared here as beta star of xt. Okay, and this is periodic boundary condition. Let's make another transformation. V of xt equals e to 1/3 of the antiderivative to this guy times wxt. Then that will reduce the equation, but w is like this. W sub t q1 w q2 w sub x w sub 3x. As you can see, this kind of dissipative term disappear. It simply just becomes a pure linear KdV equation. But here, periodic boundary condition becomes this kind of boundary condition. W0t equals eta t w1t, etc. Here, eta t is this guy, e to 1/3 of 0 beta star 1t. So, to prove our proposition 1, 2, and 3, it turns out we only need to consider this linear system, w sub t plus w3x equals f, and with this boundary condition. But here, eta 0 is greater than 1. If eta 0 equals 1, that's periodic boundary condition. But here it's important, our eta 0 has to be greater than 1. Okay, it's greater than 1. Okay. Now you may say, how about those terms, q1w, q2w sub x? Those are basically, you can this is a lower order term. It does not play a significant role. You can view this one as a small perturbation for this w3x. So to get those estimates, we can just forget about the q1w or q1w sub s, only consider this case. After get the estimates of this case, we can easily get the estimates of this case, which includes q1w and q2w sub x. Okay. So we count this. As you can see, after this variable transformation, now we reduce to consider the equation is quite simple, just a KdV equation, linear KdV equation, wt plus w sub 2x equals f. And the boundary condition a little bit weird, right? That's a little bit different. It's not a periodic boundary condition. You have eta 0 here, and which is greater than 1. Okay. And for this kind of unconventional boundary value problem, we just need to get its estimates. Okay. So we want to show that it has this our theorem 4. It's basically initial data L2 F is L1 about time. This one you have sharp cadence smoothing. Okay. If instead initial data 0 F is L2, L1 to L2, then you have strong cadence smoothing. This is continuous about time now. Okay. And then also you have double sharp cadence smooth, 0 FL2, and double sharp cadence smooth. So if you can prove theorem 4, and then that basically that equivalent position 1, 2, and 3, and then use contraction mapping principle, you can get the results for that nonlinear case, theorem 1, theorem 2, theorem 3. So here, what we left to prove is this theorem 4. Okay, but how do we prove this theorem 4? How do we prove this sharp cadence smoothing, strong cadence smoothing, double sharp cadence smoothing for solution of this boundary value problem? Okay, let's just talk about some challenging issue we're going to have for the proof of theorem 4. And then I'll show you how to get around. Okay. Now recall that to prove the solution of linear KdV equation on the whole line, to prove its sharp cadence smoothing, there are two important tools. Okay. One is Fourier transform. And the second one is Planck-Chere's theorem. Those two play key roles to get sharp case smoothing property, especially puncture theorem. Probably, as far as I know, that's the only way. Probably, I don't. Yeah, but as far as I know, this only way, most maybe I shouldn't say only way, but it's most effective way to have to prove sharp case smoothing. Let me take this example here. Okay. Solution of KdV linear KdV pure domain. First of all, you can use Fourier transform to get explicit integral representation of the solution in terms of its initial data. That's the role played by Fourier transform. You can use a Fourier transform to find an explicit integral representation formula of the solution in terms of initial data. And with that, U sub x case. And then you can do some transformation. As you can see, in fact, this U sub xt is kind of Fourier transform of this part, or inverse Fourier transform of this part with respect to t. Now, this is the inverse Fourier transform of this part. Then get L2 norm about solution of U sub x. Last time you use puncture theorem, it works. That basically becomes L2 norm of this part. So I put it here. Yeah. I'm sorry, here is supposed to add value. Here you have supposed to have a square. Okay. And then you change it back to the side, you find out L2 norm of U sub x about time simply just equals L2 norm of the initial data. This is true for any x, right? So it takes supreme value here. Look at this. So as you can see, this is sharp results because use puncture theorem. Then what you got is equality, but not inequality, it's equality. So it's absolutely sharp. You cannot prove it to any improvement, right? So again, as you can see here, two tools are important. One is Fourier transform. Its role is for us to get explicit integral representation formula. Puncture theorem, that's another key for us to get sharp case smoothing. Okay. Now, back to how about the equation posed on the periodic domain? Yeah, of course, you cannot use a Fourier transform. However, you can use Fourier series, right? And we do have explicit solution formula of this U in terms of the initial data, right? Initial data. Okay, and then you can imitate the same thing. You say, okay, I can make transformation and then find the L2 norm about time of this U sub x. But of course, immediately you have trouble because this is discrete about a Fourier series. You puncture theorem does not work here at all. Okay, of course, no surprise. We know the problem, the Cauchy problem of KdV posed on the periodic domain has no case smoothing at all. So anyway, puncture theorem doesn't work even though you have explicit representation of the solution in terms of initial data. So that's a challenging issue here. Okay, back to our axiom 4. Our problem here is posed on the finite interval. For finite interval, well, can you get integral representation of solution in terms of the initial data and forcing f? This is a challenge because you cannot use a Fourier transform. Okay, yeah, you have replace Fourier transform by something else. Secondly, can you use puncture theorem? But of course, you need to have integral representation. Okay, you cannot get integral representation. Therefore, you are in trouble here. Okay, and also Fourier transform works for whole line. Puncture theorem also works on the whole line. You cannot work on the finite interval. Okay, so that's a challenging issue. But our problem is challenging here. That our problem posed on the finite interval, and we don't know how to get at this one. Fourier transform doesn't help for us to get explicit integral representation formula. Okay, so that's two issues here. right, and then, so Fourier transform cannot apply because finite interval. Fourier series approach provides no help at all either. Okay, so how do we do that? All right, and we know Fourier transform and Planck theorem works for the question posed on the whole line. So naturally we say, can I link our problem, initial boundary value problem, to the Cauchy problem on the whole line? We try to find a link between them. Okay, so you can see this is a boundary value equation posed on the finite interval. This will be the equation posed on the whole line with no boundary condition because that's Cauchy problem. Okay, so our second step is try to find a link between those two. And turns out here we consider this sub t plus this sub this equals f star. This is a phi star. The f star and the phi star are extension of f and phi from zero interval, finite interval 0, 1 to r, and with compact support. Okay, with compact support. This is important too, with compact support. Okay. And of course, put the f star here, phi star here. This is Cauchy problem. We can solve it, right? You can use Fourier transform, find it's a solution. Okay, and without a solution, you can find a trace z0t minus eta 0 z1t. That's called q1t. Z sub x0t minus this guy I call that q2t, and this one we call q sub 3t. Okay, but of course, if q1, q2, q3 are 0, then immediately you get a solution of this guy, right? But there's no reason to say, yeah, q1, q2, q3 has to be 0. In fact, it's not 0 at all. Okay, not 0 at all. And so, okay, but anyway, I put the phi star here, and solve for z, I get the q1, q2, q3. Next, say when you for this solution is on whole line R, right? However, if you restrict it to the interval 0, 1, and the Z basically solve initial boundary value problem here. Yeah, because the restrict interval f star is f, phi star is phi, and however, z0t minus this equals q1, this is q2, this one equals q3. If q1, q2, q3 are 0, that's fine. But we know q1, q2, and q3 can never be 0 here. So what do we do about that? Then we take this q1, q2, q3 and consider this non-homogeneous boundary value problem. Pay attention here. Initial data is 0, and q1, q2, q3 come out of z. And Z is solution of this guy. Okay, we put this one as a boundary data. Then we try to solve this non-homogeneous boundary value problem. Okay, suppose we are able to solve that. With that in our hand, and then as you can see, V is solution of this one, Z is solution of this guy. This is whole line problem. This is finite interval non-homogeneous boundary value problem. And then if it is W equals Z minus V, you can see, according to our argument, the W solve this as equation, which at the beginning in our mind, we try to prove theorem 4, this equation. So as you can see, this one we find that we link the solution of this equation W with the Cauchy problem of KdV equation and the solution of non-homogeneous boundary value problem. Okay. So W equal to Z minus V. Now, if you want to get the estimate of W, what we need to do is we just get an estimate Z and get estimate of V. Instead of study W, we just study Z and V. Okay, so here's to prove this one for W, what do we need to do? Because this link, we can only need to estimate solution of V and solution of Z. But this one is whole line problem. This is one is non-homogeneous boundary value problem. Okay, you'll find a link. So let's go to our step 3. We estimate the solution of the whole line problem. Z sub t plus Z sub 3 equals F star, this one. And this one we can build up those two lemmas. Okay. And if phi belongs L2, okay, then phi star also belongs L2, of course. F belongs L1, 0t, the F star belongs to L1 about time here to 0 extension. Okay, anyway. And we find out we have estimates. That's sharp K smoothing. Okay. And then if F is L2 bar time, then you have sharp double K smoothing. And then this one a strong K smoothing. Okay. And for this thing. Remember, this is a whole line problem. Based on theory of Koenig bounds Vega, we can get these results easily with a very minor modification. And this is another key lemma, sharp traces. Because remember, we have Q1, Q2, Q3. We want to know what's the regularity there. If phi belongs L2, F is L1, and then Q1 belongs H1 third. This is L2, Q2, L2, Q3, H minus 1 third. And moreover, if initial data is 0, F belongs L2, and then Q1 has better trace regularity. H 2/3, 1/3, 2. Okay, so we got this one. This one again, because this is whole line problem, those trace estimates can follow from Koenig bounds Vega's work and easily, only with some minor modification. Okay. But anyway, those two lemmas are key lemmas for us too. Next, after find the estimates of Z, next we need to find the estimates of V. We need to start with the non-homogeneous boundary value problem. Okay, given Q1, Q2, Q3, we try to solve for V. Okay, and then here we call V is from Q1, Q2, Q3 to V. We say that okay, this is a solution operator from Q1, Q2, Q3 to V. The solution operator BDR, and in fact we call this one is a boundary integral operator. The initial value is 0, you only have boundary data. Okay, we call the boundary. I'm sorry, this is supposed to be integral operator, not the internal operator. My bad. Sorry about that. Okay, we need to start this one. And especially we need to find the estimates for this boundary integral operator. Q1 belongs H1 third, Q2 belongs L2, Q3 belongs H minus 1 third, we get a sharp K smoothing. But if Q1 is H2 thirds, Q2 is 1 third, Q3 is L2, then we get a double, sharp double K smoothing. Okay, so that's what we need. So we need to get this one too. Now, of course, this is K smoothing, sharp K smoothing. How do we do that? But in the whole line case, we know two play important role. Fourier transform and the Planck theorem. But here, of course, you cannot apply the Fourier transform. But of course, there's a finite interval. You cannot apply the Planck theorem either, right? So, but of course, the role of Fourier transform is to get an explicit integral representation of the solution in terms of its initial data, right? So here, we cannot use the Fourier transform. We say, okay, but is there any way we can find explicit integral representation of this boundary integral operator? So that's the key. We want to find the explicit integral representation of the boundary integral operator. Okay. With that kind of like use the Fourier transform, right? But we cannot use Fourier transform. We must find another way to do that. And with explicit integral representation, then probably we have chance to use Planck theorem. Remember here, we cannot get away with Planck theorem to get, if you want to get sharp case motion property. Okay. So how do we do that? That's the key. Okay. Then here, we cannot apply Fourier transform. However, we can apply the Laplace transform to the equation, this time about the t. You cannot apply x because x is finite integral, right? But we can apply the Laplace transform about both sides of the equation about t. So we get something like this. So apply the Laplace transform. This PDE simply becomes ODE with this boundary value from ODE, right? This is Laplace transform. And with that, we can, okay, solve this ODE. We find out the Laplace transform solution basically have this explicit representation. Okay, here are some little bit detail. Okay, and with this one, here lambda 1, lambda 2 are 3 roots of this solution. You can have explicit form of lambda 1, which is rho into I theta plus theta. Okay. So by using Laplace transform for time t, we can find the solution, Laplace transform of solution. Then use inverse Laplace transform, you can get the solution back. So you can get the solution is sum of those 3 terms, and each of term is like this. So you conduct the inverse Laplace transform. Okay. However, this one is not explicit enough. Then you can just use contour transformation. Okay, and you can make it more explicit. Okay. So then we have this one. Okay, and then explicitly Vxt becomes sum of so many terms here, and this have this form 1, 2, 3. But each of them, this is this one, that's integral representation like this. Okay, and this one will be like this. Okay, like this. Okay, and the third part is like this. Okay, I don't want to give in detail, but we reach our goal. We do have explicit integral representation of solution V in terms of boundary data Q1, Q2, and Q3. And the explicit form is like that. Okay. So next, what do we need to do? We only need to estimate the integral representation of like this. Okay, like this. Okay. Now, first for the estimate of this part, this is integral over a compact domain, just like this. This is a compact. So this is compact, the integral over compact domain. And of course, then in fact, this integral as a function of x and t is infinitely smooth. Infinitely smooth. There's no trouble at all. It's infinitely smooth. So estimates of this one is almost trivial. Okay, because gamma n is compact domain in the plane. One need to, it remains to estimate the integral like this. Now you can see this one basically is an integral type of like this. Okay, and this is each I rho cube t, and you can make a transformation. This is each I eta t, and then this one becomes a Fourier transform of this part with respect to t, right? And then of course, in that case, you can apply the Planck theorem to get the needed estimates. Okay. All right. And so I think this one we just give the outline of the proof here is we link the finite interval problem to the whole line problem plus a non-homogeneous boundary value problem. Okay. And for non-homogeneous boundary value problem, we use Laplace transform about time t, and which enable us to get explicit integral representation of the solution V in terms of its boundary data Q1, Q2, Q3. Although it's quite a little bit complicated, technically involved, and there are quite a few terms out there. But anyway, we do have explicit integral representation of a solution in terms of its boundary data, which we can apply the Planck theorem to get the sharp cadence smoothing property. Okay. You can find all the detail in our paper, just appeared recently, the sharp cadence smoothing property of weakly dissipative KdV equations with a variable coefficient and a pure domain. It's a discrete and a continuous dynamic system. Okay. All right, so that I can end my talk. Thank you very much for your attention. All right.
Thank you, Professor Zhang. It was an excellent talk. Now we have some time for questions. Anyone can open your microphone or ask or write something on chat. If anyone have a question, I have one question.
Yeah.
Do you know if this sharp results are still valid in some non-periodic domain?
Yeah. For non-periodic domain, basically, yeah, let me share the window here. Yeah. Let's talk about for long period, basically, it's even easier because for example, the KdV equation posed on the finite interval with the judicial boundary condition, and then that judicial boundary equation already introduced the dissipation. Okay, so you don't need to use up 2s anymore. You just simply apply the idea here, and you can use you can find explicit inward representation of the solution in terms of the boundary data and the initial data. And then from there you go the whole line. Yeah, and in fact, for judicial boundary conditions or other peptide boundary conditions, it's easier. The challenging part is for periodic boundary condition, because for periodic condition, you know KdV, you have no cadence smoothing. For Berger's equation, you don't have any sharp cadence smoothing. That's because of periodic boundary condition. You don't have any kind of dissipation introduced so there for KdV equation. So then we combine together a KdV Berger's equation posed on periodic domain, and then because you cannot apply Planck's theorem for periodic domain case to get sharp cadence smoothing. So that's the challenge of it. However, because the presence of dispersion and dissipation, then we find a way to transfer to kind of boundary value problem. You remember here that the boundary value problem here is eta zero here. Has to be greater than 1. This eta has to be greater than 1. If equal to 1, it's not going to work at all. So it's yeah. Hope I answered your questions.
Yes. Any more questions? So we can thank you, Professor Zhang, again.
Well, thank you very much. Okay, so yeah.